Hello, eighth grade math. So this is your video lesson for week 7. I'm going to go ahead and cover both pages in this video, and I'm going to be going through every question type that we have, so you won't feel alone out there. Now, before we get into it though, I want us to take a look at the second page, the one that's titled as week 7 continued, questions 6 through 8 only. I want you guys to make sure you know not to do question 4 and question 5. That's something that without going through the lessons in between, you'd be kind of lost on trying to figure out how to do. It's just a different process than you're used to. So we're just going to look at questions that you should understand how to do. All right, so let's go ahead and take a look at the start of lesson 6 here. So in this part, we're still in the last part of module 7, the last thing we're going to cover in it. And we're going to look at the difference between finite and infinite decimals. So we're going to look at how you can identify the behavior of a decimal number and identify whether it is a rational or irrational number. So I'm going to cover all of those things going over this lesson, so please make sure you pay attention. So let's start with going through what we have going on here at the beginning. And the first thing it wants you to do is it has a few different numbers, and it wants you to try to find a decimal expansion of the number using long division. So we're going to get a little bit of a practice of an old skill that will come back into play as you're in algebra and right now. So if you don't quite remember how to do it, I will go very basic with the first one to make sure you see the process I'm using. So let's go ahead and get that knocked out. I'm going to go ahead and take this over to a blank document so I have more space. All right, guys, so here we are with our first question. So like I mentioned before, there's a couple different things I want to go over on this problem. I want to show you the long division process in case it's a little rusty. And then I also want to talk about how I know this is a rational number. So let's go ahead and get started with this one. So long division, we're going to take the numerator and divide it by the denominator. So that means I have my division bar here, and underneath it I will have 54. And on the outside I will have 20. So remember, in long division, you are asking yourself how many times can the outside number be factored into the inside numbers, or how many times it can be divided by, however you like to look at it. So how many times can 20 go into 5? We go one digit at a time. Well, 20 doesn't fit into 5, not evenly. So we're going to go ahead and use 2 digits instead. So how many times can 54 be divided by 20? So if I count by 20s, I have 20, 40, 60. 60 is over 54, so 40 is where I would stop, and that is 20 times 2. So I know that a 2 would go above the 4. Now, whatever is the last digit you used, that is where you put your answer to this part. So 20 times 2 is 40. And in case you don't remember what comes next, then I'll subtract to get a remainder. So I have 54 minus 40 will give me 14 left. Now, in case you forgot what to do if you run out of digits, I don't have any numbers left, so I can't make 14 be divided by 20 evenly. So what I'm going to do is I'm going to add a decimal to the number underneath and put a decimal directly above it. And I'm going to add a 0 because 54.0 is equal to the same thing as 54. Those are equivalent. So now I can drop the 0 down and ask myself, how many times does 20 go into 140? Or how many times can I divide 140 by 20? And the answer is 7. 20 times 7 equals 140 exactly. So 20 times 7 gives me 140. And when I subtract this time, I get a remainder of 0. When you get a remainder of 0, you know that this number has ended. There's nothing left. So my answer to the first one is 2.7. So let's take that back to our assignment. Oh, wrong one. Here we go. So 2.7. Let's talk about this number for a moment. So I want to talk about what groups of numbers it's included in. So 2.7 is considered a rational number. And how I can tell that is the number can be written as a fraction. Now there's a simplified version of the fraction, this one is here, but just in general, if I can write the number as a fraction, remember that means the number is considered rational. Also, when I'm looking at the decimal expansion of the number, how I can tell if it's rational is due to the fact that the number ends or repeats, but we'll get to that on a different question. So since this number ends and there's no more numbers following this, I can say this is a rational number. All right, so now let's take a look at B, which says use long division to determine the decimal expansion of 7/8. So we're going to take it back over to our Google Doc, and I'm going to work through that one there as well for you. Okay, and now we're back, and we're going to take a look at the second one. So we have the fraction 7/8, and we want to turn that into a decimal. So once again, we are going to take the numerator, or the top number, and divide it by the denominator, the bottom number. So let's get our division bar over here. So I will put the numerator in underneath as the dividend. Oh, I totally just said that and then did the wrong number. Hold on. All right, so as I was saying, we'll have the numerator inside and the denominator outside as the divisor. So now we have to ask ourselves, can 8 go into 7 evenly? And the answer is no. So once again, we are going to add a decimal and bring it straight up. So since 8 did not go into 7, I'm going to go ahead and put a 0 as a placeholder here. So you'll want to do that every time, so just to make sure you understand it's a decimal number and not just a regular number. So now I'm going to add a 0 and then ask myself, how many times does 8 go into 70? So if I'm thinking through my multiplication facts, 8 times 8 is equal to 64. If I go one higher than that, it'd be 72, and that's too high. So 8 times 8 is the number I'm going to use, and 8 times 8 is equal to 64. I'll subtract and get a remainder. My remainder here is 6. I'm going to have to add another 0, drop it down, and ask myself, how many times does 8 go into 60? Well, if I know that 8 times 8 is 64, if I go one less than that, 8 times 7 is equal to 56. That's as close as I can get. So I'll have a 7 here. 8 times 7 gives me 56. Now, I am shortcutting this process of finding these factors because I know my multiplication facts. If you need to try a few of them on the calculator to see how close you can get, feel free to. Whatever process works good for you. But I recommend you try to remember your multiplication facts because that will make this the easiest. And then I have 4 left. I'm going to add another 0. A goes into 40 5 times. All right. Now, yes, I know that some of these are very easy to do if you just did, well, Mr. Boland, why didn't I just do 7 divided by 8 in the calculator? Well, sometimes you can't, it's still not very easy to tell what the pattern of some decimals are or to see if they end or not. So that's why we're showing this through the long division process in this lesson. Okay, so when I do 8 times 5, that is going to give me 40. And then I will have no remainder left over. And so then I know I'm done. And then there's going to be a 0 down here. So this is my decimal expansion. I have 0.875. So let's take that back. And I have 0.875. So question, did this decimal terminate or end? Yes, we came to a point where all the digits after would have just been zeros. So that's how I know that this is the end of the number, and therefore I call it a finite decimal. And it's also considered a rational number because it can be written as a fraction, 7/8. All right, so now I want to look at one that's a little more interesting. I'm going to take a look at part C, which wants us to use long division to determine the decimal expansion of 8/9. So give me a moment to get back to the other page. All right, so we are back. Now we're going to do 8/9. So let's get my problem set up. So I'm going to have my numerator inside, denominator outside. All right, so now let's get started on this one. So what we're going to do here is 9 cannot go into 8, So we're going to go ahead and do our trick where we add the decimal and add a 0. I'm going to go ahead and put my 0 up here for my placeholder. Now, how many times can 9 go into 80? 9 can go into 80 8 times. 9 times 8 is 72. Now, I was able to think of that one pretty easily because 9 times 9 is 81, a perfect square. So we're just one below that, so it had to be one below that as well in my answer. 9 times 8 gives me 72. Let's subtract for our remainder, and I'll have an 8. Okay. Once again, let's add a 0. Drop it down. How many times does 9 go into 80? Well, that's the same number again that we just used up here. So we know it's going to be an 8. 9 times 8, once again, is 72. Subtract, and we'll get a remainder of 8. And hopefully by now you can notice that we're just going to rinse and repeat over and over again. So there's just going to be 8, 8, 8, 8, 8, 8, 8. It is a never-ending decimal. So when you have a decimal that is never-ending, you need to check for a pattern. If there is a pattern, like in this one, what we will do to write our decimal, in case you forgot, is I will have 0.8, and then I'm going to put the repeating bar over it. Now, let's say there were multiple decimals that were being repeated, like it was just throw random numbers pulling out of my head here. What if it was 130, 130, 130, on and on like that? So in that case, I would not just put a repeating bar over the 1. I have to put it over each decimal that's being repeated in the pattern. So it would look like this. So let's write out the example I said. If I had this as a repeating decimal, 130, 130, 130 over and over again, and I'm going to put this here to show it continues forever, then how I'd write that as a decimal is, in simplified way, is 0.130 with a repeating bar over all 3 digits after the decimal. So like that. That is how I'd write that out. So with that cleared up, I am going to leave part D on this page for you guys to do on your own and go through the same process. So since this decimal never ended, would I call that a infinite or a finite decimal? So that one I would call infinite because the decimal continues going forever. Okay, now from here, let's go and move on to our second page. All right, so here are our last few questions. So now we are trying to identify if some of these infinite decimals are considered rational or irrational numbers. So irrational numbers that is our group of numbers that we cannot write as a decimal, that it's still part of the real number system, but it is not included in the groups of rational, like counting numbers, integers, whole numbers, like those. It is in its own subcategory because it does not fit in with the rest. So I'm going to take a look at each one of these, and we're going to go through the process of determining if it's rational or irrational. All right, so now let's take a look at number 6. Is the number 9/11ths, which is equal to 0.81818181 repeating, rational? And wants us to tell them why. So this number right here, this is the dead giveaway for if it's rational or not. If a number can be written as a fraction, it is a rational number. So we know the answer here is going to be yes. And we can explain ourselves by saying that it is a repeating decimal, or that it can be written as a fraction. Both would be a good explanation. So I can say yes, it can be written as a fraction. That is what I'm going to say here. All right, let's go ahead and start thinking about our next one here. Number 7. Is the number the square root of 3, which is equal to 1.73205080, and then it continues on forever. That's what dot 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 means. Is that considered rational? So first thing I'm going to look for here is I'm going to ask myself, is this written as a fraction? I do not see it obviously written as a fraction. So since it's an infinite decimal going on forever, and I don't see that it is a fraction, I would look for any kind of pattern, and there's clearly no pattern. It's just random numbers over and over again. That is how I can recognize that it is an irrational number. So when it asks me, is the number square root of 3 rational, I would say no, because it is a repeating decimal with no pattern. I'm sorry, I should say an infinite decimal with no pattern. Use the wrong terminology there. All right, and then I'd like for us to do this last one together. So look through number 8. And think about the process we used on 6 and 7, and go ask yourself how you can tell if that is a rational or irrational number. Did you start by checking to see if it's written as a fraction? That's where I would always start. Now that you see it's written as a fraction and that it is a repeating decimal, you can say, yes, it is a rational number because it has a repeating decimal. Just going to put no pattern here on the last one. Apologies, guys. I'm having a real hard time writing on this one for some reason. All right, so just to make sure everybody's on the same page, yes, we can say this one is rational because it has a pattern of a repeating decimal, and it can be written as a fraction. Even though it's a pretty wild fraction, it still counts as being written as a fraction. So that covers those 3. So that the big takeaways I want you to have from this video is being able to tell if it's a finite or infinite decimal based off of its decimal expansion, making sure you understand how to read that, and then also being able to tell if a number is rational or irrational. So once again, just to make sure you're familiar with the word, if I were to write out irrational like I would on number 7 to describe what kind it is, it's written like so. But some of you guys wondering how to write that word, so I'm going to put it here. This is how I would spell irrational. Use the prefix ir. So it's irrational. That is the opposite of rational. All right. So that's everything I wanted to go over for this. If you have any other questions or are confused about anything, please let me know. This is going to be the last video lesson I put out for you guys. So pretty much the rest of the time, you guys just need to be focusing on getting in your assignments and then asking me any questions about any you have so you can get that finished up. All right. And I hope to hear from you guys soon. Have a good rest of your day.